actors in our play are hydrogen atoms. The name of the play is Falling. The date is time, and the theater is space, and we're unpaid performers. Now we need to know how much stuff there is in the universe. Suppose we ask how much stuff, on the average, there would be in 1,000,000,000 cubic miles. That's a box, 1,000 miles that way, 1,000 miles that way, and 1,000 miles that way. In that big a box, how much stuff would you expect to find? Enough to make a cow, an Airedale, a mouse, a butterfly, a diesel engine, a battleship. Come on, some suggestions.
I'll go for about five solar systems.
5 solar systems.
Yeah.
Well,
Oh, a billion.
What?
Oh my God, I'm out by a factor of 10. Sorry.
No, you're not.
I'll go for butterfly.
Well, you're a lot closer than he is. There's about enough stuff probably to make a mouse. I once told a minister that the density of this universe is only 20 drops of water in 1,000,000,000 cubic miles. I said, that's all the creation the good Lord came up with, and it's no big thing. Now, I recommend that you don't mention that. So now we want to know what would happen. Well, let me ask you this first. If we started with nothing but hydrogen and waited a long time, would we get school kids chewing gum? You get to vote on this. You get to vote on this. I'll let you think of it for a little while first, and then we're going to have a show of hands. How many think that if we started with nothing but hydrogen and waited long enough, we'd get school kids chewing gum, and how many think we would not? So how many think we would not? Please put up your hands. How many think we would? Please put up your hands. Now the rest of you are pure gold, yellow to the core. Now when I ask you for a show of hands, here you only have 2 choices. This isn't a multiple choice. This is 2 choices, and I want to see your hands on one side or the other. Whether you think that if we waited long enough we'd have school kids chewing gum, how many think we would? Please put up your hands. How many think we would not? Please put up your hands. Well, if I had asked that question to a scientific audience 50 years ago, the answer would have been unequivocally no. But if I ask that question to a scientific audience now, and I do it every now and then, the answer is yes, that's what we got. They don't just say yes anymore. They say yes, that's what we got. They do that on your side of the border and on mine. All right. So now we want to know what would happen if we started with hydrogen. What would happen to it? If we just started with spaced out hydrogen, what would become of it? Don't just sit there. You're running this class.
It would just float.
What?
It would float in the atmosphere.
It would float? No, floating means you're on something more dense in a gravitational field, and you're less dense and you're on top. And that's not the situation here.
Well,
it's true that on the Earth, the basalt floats on the iron, and the granite continents float on the basalt. And then we've got a little bit of water on the top, and then a little bit of atmosphere. This is a floating operation. But the moon isn't floating out there. It's orbiting.
So it hydrogen coalesce?
The hydrogen will coalesce. Do you understand that? It's going to fall together, because gravity is going to do its thing on it. Now the question is whether it's all going to fall together to a single cloud, or here a cloud, there a cloud, everywhere a cloud, cloud, old MacDonald had a universe. So now you get to choose on this one which way you think it's going to go. How many? And I want you to go to one side or the other. This is not multiple choice. I want to know how many of you think it's going to all fall together to a single cloud? Please put up your hands.
Eventually.
How many think it's going to go to a McDonald universe? Here a cloud, there a cloud, everywhere a cloud.
At first.
When we look up with the telescopes, we can see right away that it's a McDonald universe. We have these huge clusters of galaxies. Don't brag. We have these huge clusters of galaxies, and then we have galaxies. Now we want to know which is going to fall together first, little clouds or big clouds. So we're going to do a little tiny bit of arithmetic. We're going to have a big cloud. This is our big cloud. And we're going to have a little cloud. This is our little cloud. And let's just say that this one has twice the diameter of the little one. And we want to know which one is going to fall together by gravity first, the big one or the little one. And we're going to say that the density is the same throughout those two clouds, and this one's twice the diameter of that one. I want to know which one is going to fall together first. Let's say this is the middle of this one, and this is someplace on that one. And this is the middle of this one, and this is the corresponding place on that one. And we want to know whether this one's going to get in here before this one gets in here. Now you're going to have to vote again, you know. You got to vote for. Well, there's a third choice. This is a multiple choice. You got the little one, the big one, or a tie. That's all you get. The little one, the big one, or a tie. All right, how many for the little one? Please put up your hands. How many for the big one? Please put up your hands. How many for a tie? Please put up your hands.
Oh, I missed it.
Well, I think the tie wins it, but not by very much. Now we're going to ask ourselves which way it's going to go. First, we need to know, does gravity pull harder when we're closer or when we're farther away?
Farther away.
Well, you flunked that one. Gravity pulls harder when we're closer. Otherwise, the moon would come right down. Gravity pulls harder when we're closer, and I'll tell you how it works. Oh, no. You have to tell me how it works. If the moon were twice as close, how much harder would we pull it?
4 times.
4 times harder. And you can remember that by thinking of a lamp. If a lamp looks that big where you are, then if you went twice as close, it would be twice as wide and twice as tall, or 4 times as big on your side and 4 times as bright. Is that dreadfully clear? It would look 4 times as bright if you went twice as close to it. So gravity and electricity are all-American forces, and they operate like that. If you go twice as close, they get 4 times as strong. And there aren't any other all-American forces. There are only gravity and electricity, which are all-American forces, no others. Yes?
On CBC's Quirks and Quarks about a month ago, there's a woman talking about a force that increases the further away.
Well, there aren't any. I don't care who she was, and I don't care what she said.
She got a Nobel Prize.
I don't. Now, you can't threaten me with the Nobel. When I was in college in 1934 and 1935, Chandrasekhar did his work in 1935. He got the Nobel Prize in '83. Now, in case you think they're all smart over there, he did his work in '35, got the Nobel Prize in '83. Okay. Just in case you think they're not retarded. Einstein did his work in 1905, got the Nobel Prize in '23. Not for relativity theory, for quantum mechanics, which he couldn't stomach. All right. Now, when we consider distance alone, since this one's twice as close, it's this one gets pulled 4 times harder, right? We're just considering distance, nothing else. Just distance, this one's twice as close, gets pulled 4 times harder, so we'll multiply it by 4 up here times 4. This one has more stuff in it. How much more stuff? Keep going. 8. They do the same thing to you in Canada that we do to the kids in the States. We let them out of kindergarten before they finish playing with the blocks. If you ask a kid, to make this big a cube, out of this big cubes, he'll grab a whole handful. It takes 8. 2 floors of 4 each, no? 2 floors of 4 each. All right. This thing is twice as wide this way, twice as wide that way, and twice as wide this way, so it's times 8. So the amount of stuff doing the pulling here is times 8. So altogether, when we do our arithmetic, it's the big one times 2. It's the big one times 2. That is to say, this one is pulled twice as hard as that one, but it has twice as far to go. And both clouds fall together at 4:35 in the afternoon. Is that clear? The physicists have a word for this. There are seats in here. I think there are 2 in there, and there's 1 up here. And it's just as warm up here. It's probably a little warmer.
A little warmer, I'd say.
So the physicists have a word for this. They say that the free fall time is the same for clouds of all sizes if the density is the same. And right now, at the density of the sun, the free fall time is 3/4 of an hour. If nothing kept the sun from falling together by gravity, it would collapse in 3/4 of an hour. And then in another 8 minutes, we could see it. Okay. So we don't have any way to find out which cloud is going to collapse first, the little ones or the big ones. But we left something out. We left out the breezes. There's no reason to assume that all the hydrogen is going to be standing still. Now suppose there are little breezes going this way and that. Which size clouds will be more upset by the breezes? The little ones or the big ones? Big ones. You get to vote again. Now remember, in this class, you vote with impunity. It's not like voting for some politician and getting the wrong guy. Here you vote with impunity. I want to know what you think. So how many think that the big clouds would be more upset by the breezes? Please put up your hands. How many think the little ones would be more upset by the breezes? The little ones, of course, you silly geese. We can always, remember, the pull of the particles goes up linearly with the diameter. If the cloud is 1,000 times wider, the particles are pulled 1,000 times harder. And we can always find a cloud big enough so that the wee breezes don't make no never mind. Okay? Is that clear to you all? I'm here to make this perfectly clear, and you're here to see that I do. Now, if I don't say it so that you can understand it, please get on my case.
Wasn't the gravitational force less the further away you got from the middle?
Yes, that's true, but there's more stuff pulling it.
Okay.
And it happens in both clouds. It happens in both clouds. But that's not the problem here. The problem is that the particles in the cloud get pulled in proportion to the amount of stuff between them and the middle. And the bigger the cloud, the harder they get pulled. So we can always get a cloud that's big enough so that the breezes cannot upset its collapse. We can always get a bigger cloud. So what we see when we look out with the telescopes is these enormous clouds. Now when a big cloud like that collapses like this, does the density go up inside? If it collapses to half its diameter, how much does the density go up? 8 times. 8 times. So if it collapses to 1/3 of its diameter, it goes up 27 times. Is that clear to you all? 3 times 3 times 3. All right. So it's just a question of time before one of these great big clouds gets small enough so that smaller clouds can condense out to the side because the density has gone up. Is that clear to you all? As these great big clouds condense, the smaller clouds can form inside and condense out. And when they condense out, smaller clouds smaller clouds inside of them can condense out, and it goes right on down to stars. What we see when we look out with the telescopes is these huge clusters of galaxies, curdled to galaxies, curdled to clusters of stars, curdled to stars. Now the question is, are the stars curdled inside? Is the sun a star?
Yes.
Yes. So you have a close example. Are the stars curdled inside? This is a yes or no.
Well, what would be not curdled? Like, what's...
Well, I don't want to give it all away, but the ocean isn't curdled.
The milk is curdled.
If you put lemon in the milk on the stove, it'll curdle.
So the sun is
You understand what curdle means?
Not uniform?
It lumps up so that you got something in between the lumps, yeah.
Okay.
Lumps up with something between the lumps.
The sea is curdled, though.
What?
There are particularities in the sea, differentials in the ocean.
Well, it's not curdled.
It doesn't have southern membranes, but
If I had a custard as smooth as the ocean, nobody would complain about the lumps.
Just the temperature.
if you had a custard as large as the universe, you wouldn't complain about the lump either.
What was that?
If you had a custard as large as the universe, you wouldn't complain about the lumps either.
All right. So the question is, how many of you think the sun is curdled internally? Please put up your hands. How many think it is not curdled internally? Please put up your hands. It is not curdled internally, and you could tell right away if you knew what the gravitational field at the surface of the sun is. It's nearly 30 times the gravitational field at your lake. The gravitational field at the surface of the sun is nearly 30 times the gravitational field at your lake. And how many of you ever went down to the lake to dig holes in the water? Okay. If you dug a hole in the sun, it would fill right up. 30 times faster than they fill up at the beach. So the stars are not curdled inside. No, yes?
Well, what about sunspots?
They are not curdles. They are not lumps. They are just places where it's a little bit cooler. Hotter than a welder's arc, but cooler than the rest. And they're not holes. And they're not lumps. They're just places where the magnetic field comes out through the sun, unscrums the heat motions, and impedes the rising of the hotter gases from underneath. So that's a magnetic problem. I call them magneto-hydrodynamic zits. We'll get to that.
You're saying there's no density differences in the makeup of the sun?
Yeah, no, well, I don't say that. No, there's some density, but it goes more and more as you go farther in. Less and less as you go to the outside. But the density of the sun is nearly twice the density of water. It's the density of very thick maple syrup. Very thick maple syrup, I think, would float in the sun. All right, now where are we? We're all the way down to the sun. All right, now it's time to talk about how a galaxy-sized cloud would form a galaxy. Okay? We're going to erase these even density things. Suppose we have a galaxy. Do you think the density could be less and less as we go out? Yeah. So far as I know, the entire American public agrees to this. And probably the whole Canadian public also agrees to this. But there's a reason for it. The hydrogen falling this way, falling in this way, has collided with the hydrogen falling in this way. And they can't get past the middle. So of course it piles up in the middle. So of course the center is more dense. So where are clusters of stars going to form first? In the middle. This part is going to break up into clusters of stars, see? And then we're going to have clusters forming in some of these outer places like this. Now, suppose we have a cluster, say, up here. What's it going to do? It's going to go towards the middle. Is it going to go faster and faster? Yes, it's going to go faster and faster. What's it going to do when it gets to the middle?
Slow down.
It's going to collide with the stars coming from the other side.
Now don't forget, the density of this universe is 20 drops of water in 1 billion cubic miles. Now you have each of you to think how much loneliness was left behind in this universe by your particular body. Just think of it.
But our bodies are so, we get all the gravitational waves and stuff, we make quite an impression out there.
But we're talking about how lonely these stars are.
But aren't we in contact with all of them with our gravitational waves and all that?
Yes, but that doesn't cause you to fall onto Jupiter very quickly.
But
We're talking here about how lonely stuff is. Even in our solar system, the stuff is lonely enough. But when you consider how lonely the stars are, it's something like maybe 3 golf balls in the continental United States. No, the continental North America, never mind the United States, we're just a little place. Continental North America, maybe one up in Alaska, one in Florida, maybe one down in Mexico or something. Passing each other once in many millions of years and not about to say, how do you do? That's the density of the space where we're living now. And we're right in the disk of a galaxy. And the spaces between the galaxies are unthinkably empty. So you have to understand that the stars are very lonely and they're not about to collide when they go through the center. They're not about to collide. The number of stars in our galaxy, they think, is equal to the number of grains of wheat, 3 feet deep over an 8-acre farm. And they've been around for at least 15 billion years, and the astronomers figured that by now no 2 stars would have collided. And they move around at these awful speeds of 20 and 30 miles a second. Our sun is headed for Vega at 13 miles per second. So, what are they going to do when they get downtown? They're not going to collide.
They're going to shoot on through.
They're going to coast on through. We have a good word for it in English. It's called coasting. It's going to go lickety-split to the center, and then it's going to coast on through. Now, if it's formed into stars here, how far through on the other side will it go?
I just want to hit you on, I'm still not clear that they're not going to collide. And I want to know why they're not going to collide.
Just because stars are too bloody lonely to collide, that's all.
No, I won't. Do they not all have gravitational?
If you had a friend throw a super ball from the other side of the lake over toward Kaslo, and you threw a super ball from this side over that side, the chances of collision are calculable, but it's lots higher than this likeliness.
I mean, it doesn't matter how thinly they're spread.
No, it doesn't.
If we're talking
it does matter how thinly
they are going to.
It does matter how thinly they're spread, and they made it that thinly. They are thinly spread. They're very thinly spread. Just in case you have any doubt about it, wait till it is dark and look out into the night sky, and remember that most of those things are brighter than the sun.
But if I was that lonely and thinly spread out, I mean, I would want to hit something head on.
Well, if you were that spaced out, I don't know what we would do with you.
But don't they also attract one another? Isn't
Yes,
there
they
gravity
do.
at work?
Yeah.
I mean, eventually, if we're talking an infinite universe, or are we talking an infinite
I
universe?
didn't say anything about an infinite.
Because if we were, they would collide.
Who said?
I did.
They go into binary orbit.
Who told you they go in an orbit at all?
Because they like to dance.
If this thing fell to the center, how far through on the other side will it go?
Same distance it was already.
No, it will go farther because it was already on the way in when it collected into stars. So it's going to go farther out on the other side, then come to a stop and fall back again. All right, now we're going to have a detour. We're going to pretend that the astronauts are on the moon. and that they have dug, these are American astronauts, and they've done dug a tunnel all the way through the moon, a 4-foot tunnel from the North Pole to the South Pole. The Russians are at the South Pole, and the Americans are at the North Pole, and they got this 4-foot tunnel dug all the way through the moon, and it's lined with clean white Teflon. And they have a clothes bar hanging across the American side, and one of the astronauts is hanging there with his spacesuit on, and he very carefully lets go. What happens to him?
He goes to the middle.
He goes to the middle. What happens in the middle?
He did all the inertia. He's traveling. He's zipping along.
What happens in the
Did he
middle?
start oscillating back and forth and never get out of the tunnel?
What happens at the middle?
It's going.
He keeps going. Where does he stop?
Not quite.
He stops at the other edge. Head first or feet first? Feet first.
That's American.
What happens to him after that?
The Russians grab him.
What?
The Russians grab him.
He goes back again head first. Can he grab the bar again?
I don't think so.
Yes, he can. He can grab the bar again. I was very clever. I did this on the moon, where we have nothing in the tunnel.
Oh.
There's no air in there. And if nobody drops a wrench in from the other side, he can grab the bar. All right. Now, I'm going to have him blindfolded. He's going to be blindfolded. Can he tell when he passes the center? You get to vote on this. He's now falling through, going lickety-split past the center, and I want to know whether he can tell when he passes the center. How many think he can? Please put up your hands. How many think he cannot? Please put up your hands. He cannot. How many think that he can tell when he gets to the other side, feet first, and turns around and comes back again head first? How many think he can tell when he gets to the other side? Please put up your hands. How many think he cannot? Please put up your hands. He cannot. He's in the state of free fall as soon as he lets go of the bar, and he doesn't feel any pull. If you're in the elevator and the cable breaks, can you lie down on the floor? No, you cannot lie down on the floor because you're falling at the same speed as the elevator. I know, you're used to being in elevators that aren't falling. That's how come you came here. All right. So this thing is going to fall lickety-split to the center, then coast on through, and then back again and coast on through. Now they're going to be doing it from all sorts of directions. Now down in the middle, we're going to have lots and lots of clusters of stars. Let's see, where's that book over there? Get me that book, please.
Nothing's going to collide.
It's right there.
Still.
Chris?
It's still.
Yeah. And I haven't yet put it in the chair. But I have a brush. Right? 56 was the first one? This is a cluster of stars. They shouldn't be pink like this. That's just metal pieces. But you see, this is lots and lots of stars, about 500,000 stars in a bunch. And it's one of these guys, okay? One of these guys. But down in the middle, there would be a whole flock of these guys, and they would scatter each other's stars around because they'd be all right next to each other. And they'd be going very slowly, because these are formed after the hydrogen has slowed down. Got it? These are formed when the hydrogen is still falling in. But these are formed after the hydrogen has come more or less to a stop. So these clusters would be right next to each other, scattering each other's stars around, till the whole central bones of the galaxy becomes one big cluster. But farther out, they'd be like this, falling toward the center and coasting on. You remember the other numbers, please.
Why did the hydrogen slow down? Why didn't it just keep flying through? You said
Because the hydrogen cloud is too bloody spacey and they collide. That is why. The hydrogen clouds are way too big and they collide with each other. But if you let it condense into stars first, it would never have made into a galaxy. If you tried to make a galaxy out of stars, they would just miss each other and go right on through. There's no way to make a galaxy out of stars, in spite of what some of the astronomers think. There's no possibility of making galaxies that way. The hydrogen clouds collide and the entropy goes up. Now, how many of you know what entropy is? Please put up your hands. Probably only a few of you. How many do not know what entropy is? Please put up your hands. Thank you. One of you would have been enough. Entropy is a measure of the scrambledness of the energy. It's easier to scramble an egg than to unscramble it. If you see in the movies that she's stirring it the wrong way and the yolk separates from the white, and she gets the shell and puts it back in the box, you'll know it's going backwards, okay? Or if you see the water come up off the deck and throw the guy up under the diving board, you'll know it's going backwards, okay? The energy tends to get scrambled and it does not get unscrambled anymore. And that's called entropy, yes?
Oh, okay. Oh, sorry.
The scrambledness of the energy tends to go up and it doesn't tend to go down. I'll give it to you in the original German. Die Energie der Welt bleibt constant. Die Entropie strebt einem Maximum zu. The energy of the universe remains constant. The entropy strives to a maximum. The scrambledness of the energy goes up. Now, when the hydrogen clouds collided with each other, the scrambledness of the energy went up. And it can never be used to get the stuff back out. Now, if it weren't for that singular characteristic of energy, that it gets scrambled all the time, we would not have any galaxies, we would not have any stars, and we would not have any living organisms. All of these things depend upon the fact that the entropy goes up. I know every generation has complained about the good old days. Your generation also complains about the good old days, and the next generation will do likewise. So if you want to enjoy the good old days, do it now. These are the good old days. Just you wait and see. I've already waded through several layers. All right. So what do we need to talk about next? Oh, yes. I know what we need to talk about next. We've talked about the circle ball stars and the globulars. What does the remaining hydrogen do that does not get formed into the stars? And I'll tell you right away, it's most of it. Maybe 10% forms into the stars, and maybe 90% doesn't. And where does the 90% go?
I thought it was colliding with other hydrogen clouds.
Well, you might say so, but where?
In the universe.
Well, of course it's in the universe. Where else is there?
Well, doesn't where it goes, doesn't that depend on what it was doing when we so-called started?
Yes. Well, this is that famous teenage question, you know, where are you going? Out. What are you going to do? Nothing. So I want to know where it's going to go. What it's going to do.
Well, it's
If
all
you
gonna be
have heard
attracted
that,
to
you're
each
about
other.
to. What?
It's all attracted to each other.
Yes.
So it's all gonna, unless I go to the ball up.
So you might think it would all fall toward the center. The difficulty is that when the stars begin to shine, they blow all the rest of the stuff away. All the stars have what we call stellar winds. Get yourself a chair if you want to look through there. There's a chair up here that's just being wasted. The stars have what we call a stellar wind blowing away from them. And so for that reason, the remaining hydrogen cannot fall into the central bulge. The stellar winds of the central bulge will blow it away. The stellar winds of the globulars will blow it away. So where does it go and what does it do?
It would set up convection cells.
You've got a heating mechanism. The exterior decorator has to turn on the heater for you.
No, when something gets pushed one way, then something's going to get pulled the other way, right? Every force or
Gravity sucks. Electricity pushes.
Well, there's 6 forces at work, at least.
They're what? Never mind forces. The universe is not made out of forces. The universe is made out of energies and not out of forces.
Like George Lucas.
So where is the remaining stuff going to go?
Some of it's just still floating out there.
What?
Some of it's just still floating out there.
Well, at least it's going to be driven out. I'm not going to use the word floating because floating is not the word here. But it's going to be driven out. The question is there a place where it could stop?
Where it started.
What?
Where it started.
Where it started? No. The entropy will not allow it to go back where it started. The entropy will not allow that. Now, from inside here, the stellar winds are strong enough to blow it out. The question is, does the intensity of the stellar wind fall away with distance faster than the gravitational pull inward? Gravity is pulling inward, and it falls off inversely as the square of the distance. If you go twice as far away, it pulls only 1/4 as hard. The question is whether the stellar winds fall off faster than that or less fast.
Seems like it would
That's fast.
go faster.
It falls off faster because gravity is pulling back on it, don't you see? Gravity is pulling back on the stellar winds, so they have to fall off faster with distance than gravity does. Because there's something to slow them down. If there wasn't anything to slow them down, they would fall off the same as gravity. But there's new hydrogen falling in from outside to slow it down, and there's gravity pulling back from inside to slow it down. So somewhere out here, gravity can win it. Got it? The stellar from inside that region, the stellar winds can blow it out. From outside of that region, gravity can pull it in. So somewhere way out here, we're going to have what I call a hovering layer, okay? Somewhere way out here, the stuff has permanent parking permits. Got it?
All right. So, John, I still have a lot of problem with gravity affecting the less dense particles, but not affecting the more dense particles. In other
Gravity
words,
affects them all the same way.
well, the 2 Gulf poles whipping across North America back and forth are eventually going to collide. Right?
That depends upon whether the universe has an infinite length of time.
Uh-huh. And we got a lot more than 2 Gulf poles too, you know. I mean, no matter how thinly spaced the major masses are, aren't they always trying to attract one another?
Yes, but they fail. You see, the moon's been attracting the Earth all these 5 billion years, and it's gotten nowhere at it. It's going away. The Earth's been attracted to the sun for all these 5 billion years, and it's not going any closer to the sun. You must have noticed.
Well, I thought that the planets were all coming towards the sun is what I thought.
Oh, you did you?
I may have
And that's
thought wrong.
why we have this global warming. Well, that's not what's happening.
No?
No.
Okay.
Oh, thank you. This is the oxide of intergalactic gas. I was at a restaurant the other day in Vermont, late at night. Waitress asked what I wanted to drink. I said, I'll take the oxide of intergalactic gas. She looked very puzzled. I said, water. And she gave me the funniest smile through the side of her face. All right.
Question?
Question.
What?
John, can you go back to the hovering layer? Does that mean that the hydrogen molecules that are coming out stop there and they don't start getting pulled back in again?
They're pulled back all the time, but they can't get away because the stellar winds are blowing them out. They can't get away because gravity's pulling them in, and they can't go in because the stellar winds are blowing them out. That's why they're stuck here. Now the interesting thing is that if the overall cloud has a spin, it's going to show up now because all the little breezes can die down in the hovering layer. All the little breezes running this way can run into all the little breezes running that way. And then if the cloud has an overall spin, what will happen to the hovering layer? You got to be louder. My ears are
It'll turn into a disc.
It'll go down into a disc. Is that clear? Now I have an ugly illustration for this. I use these ugly illustrations so you won't forget them. Suppose you have a basketball all covered with grease, and it's all covered with slugs and snails, and we spin it. Where will the slugs and snails go?
On the equator.
They can't fly away because they got their feet down in the grease.
Well, then they wouldn't have enough friction to stay on.
Their feet are in the grease. They can't slide off. They have suction cups underneath. They go to the equator. They go as far away as possible from the polar axis from both sides until they accumulate in the equator. Now the same thing happens here. We're going to have this thing spinning like this, you see? So it's going to peel away like this, and it's going to peel away like this. So in this region and in this region, stars can form again. Because once again, we have a mechanism for condensing the stuff. Did you see what happens? Now give me my next picture, please. Thank you. This is a galaxy. It is a galaxy. And this is not a nice picture of it. This is way overexposed. This has very dark, dusky disks, you see. And it shouldn't look like this at all. But at least you can see that it has a disk. And the disk is fairly flat. It's lots flatter than it looks in this picture, because this is not a good picture. The central bulge is not very flat, but the disk is flat. Now you can find the next picture. I forget what was that. So, one thing I haven't told you about the stars is that great big stars get old very fast. And when a great big star gets old, it blows up. But by the time it blows up, it's no longer made out of hydrogen and helium. It's made out of all sorts of heavy elements, and they get blown all over the galaxy. And the real heavy elements like gold for our teeth and platinum for our crucibles, that's formed in the explosion and gets blown all over the galaxy. So, remember I told you the three ingredients, hydrogen and helium and the dust of exploded stars. Now the dust of the exploded stars gets blown out to our hovering layer and flattens into the disk. And if that had been a good picture of that galaxy, and I'm very sorry that it's not a good picture, you see I have these nice pictures which I bring to the classes in the Bay Area, but I couldn't carry them all up here. I depended upon getting some other pictures, and I forgot to ask when we were at Grandma's house. Anyway, the dust of the exploded stars show up in the disk. Now, if this were our galaxy, which of course it is not, where is our sun? Out in the boondocks or downtown?
Downtown.
We're way out in the boonies. We're way out here in the boondocks. We're nowhere near downtown. The stars downtown are made of nice clean hydrogen and helium, and there's nobody like you there. You're not made out of hydrogen and helium. You have a little bit of hydrogen in the water in your body and stuff like that, but you have no helium, and you're made out of the dust of exploded stars. Our bodies are made of the dust of exploded stars with the admixture of hydrogen. Anyway, so we're way out in the boonies like this, and we go around the galaxy once in 200 million years. All right, now you can ask me some questions.
Would you say that again, please?
We live way out here in the boonies.
Yes, about 200 million
And we
years.
go around the galaxy once in 200 million years. Last time we were where we are now, Half Dome in Yosemite Valley was molten under 11 miles of stone.
200 million years ago.
200 million years.
There was a place called Earth.
There weren't any people talking English.
No, no. It might be from the movies, but I'm not.
What causes the spin?
What?
What causes the spin of the universe?
Oh, well, when I show you the slideshows, then it'll be very clear to you, because I have some computer-generated pictures of galaxies passing in the night, and you'll see right away that if they pass each other, they spin each other. Now you see, if we were on ice in our sneakers, not on skates, but in our sneakers, and you're walking by this way, and I'm walking by this way, but we accidentally bump at the shoulder, I'll be spinning this way, and you'll be spinning this way. We'll both be spinning the same way. Because the situation is that the two of us are already spinning this way, and if we bump, we just spin that way, all right? So, the galaxies, when they pass each other, they spin each other. And since galaxies are born in bunches, and not one at a time like you and me, okay? You don't have a twin? Neither do I. All right. We're born mostly one at a time. Galaxies are born in bunches. They are not born one at a time. There's no way to get them born one at a time. And stars are not born one at a time either. So for that reason, you can expect them to be spinning.
What makes them move to begin with?
What makes them move to begin with? Gravity. Gravity makes them move to begin with, if there was a begin with. We don't know whether there was a begin with. But at least gravity is the prime mover. Most of the energy available in the universe is gravitational, and that causes these things to fall. And all these things that we've been talking about so far are the result of these falling togethers. But if they miss each other like that, then they spin each other like that. And now some people ask me, are they all spinning the same way? No, they're not all spinning the same way. That would mean the whole universe is spinning. And with respect to what? Could the whole universe spin? Now, you see, there's this question. Does the total momentum of the universe add up to zero? Or is the universe going somewhere? And the answer is the universe is all dressed up with no place to go. There is no other place that the universe could go to. All right. You want to ask me some more questions? Go on, ask me some more questions. I want this stuff dreadfully clear. Really, I want it dreadfully clear. I'm about to ask you some more questions. You can save yourselves for a few more minutes. Yes?
I think I don't know anything about this, so I really, were galaxies formed?
Just by gravity, just by falling together by gravity like this. That's all that's happening. It's just hydrogen and helium falling together by gravity to galaxies and stars. That's what exists here to a first approximation. All right, now, another question? Go.
I just won't let go of this nothing collapsing, you know, I mean, or nothing colliding. If gravity is really concerned about making
you can consider that the galaxy is a big collision then.
No, but I mean, doesn't it seem to you that you're telling us things that aren't consistent?
No, because I remember what it would be like if we were out between the stars and couldn't find anything to touch.
But, I mean, the forces of these two stars, even if they're across the lake or across the continent or across the universe, are affecting each other.
Did you ever see anybody with their hands stuck together by gravity?
No.
That's fine.
But their hands can collide and then go apart.
Yes, they can.
Or their hands can collide and then disintegrate, or all.
No, they don't disintegrate, but they fly apart. But the whole thing is done by electricity and not done by gravity.
Oh.
All these things that you do and all you're talking are electrical things. They're not gravitational things. None of them are gravitational things.
And the movement of this field?
Now, does your body have a gravitational field?
Yes. Probably,
Yes.
yes.
One of the things that I've always wanted in my slideshow, like I told you, is me standing on a great big scale that would read my weight, about 140 pounds. Take a picture of me. Then turn the scale over and I stand on it again. It'll read 140 pounds and we'll take a picture of it again. And we'll show both pictures with the scale right side up. In one case it's how much I weigh in the gravitational field of the Earth, and in the other case it's how much the Earth weighs in the gravitational field of me. If you didn't have a gravitational field, you would not be able to read gravity. Only gravity reads gravity. Only electricity reads electricity. But the density of the universe is way too low to have all these collisions which you apparently imagine in your mind. We do have some collisions. It's not as though we don't have collisions, and galaxies pass each other and reshape each other, but they don't exactly collide. The gas clouds in them can collide, but the stars don't collide. Yes?
You answered it already.
What?
You answered it already.
Oh, all right.
Maybe can you explain that this was electric energy?
What?
I didn't understand that. You said.
I said gravity sucks and electricity pushes. Yeah. Gravity pulls things together and electricity pushes them apart.
I think she's asking about the electrical energy.
Oh, when you do all this stuff?
Yeah.
You're not running on gravity, except when you're falling downstairs. The rest of the time you're running on electricity. You eat all these things and you huff and puff on the oxygen and you run on the electrical energy from the chemical reactions. It's all electrical energy. Yes?
Could you talk a bit about time?
What?
You said you've used 200 billion years, I believe.
For the length of
I
time
just
it
wonder
takes.
about how long all this stuff you're talking about occurs in the spectrum of time, and I don't have any picture of it.
Well, 200 million years is not very long compared to the age of the solar system. We're nearly 5 billion years old. Nearly 5 billion years old. 1,000 million makes a billion. A million is a little dinky thing compared to a billion, and we're nearly 5 billion years old. Yeah?
Do you think this process has a beginning and an end, or is it continuous? Creation of the universe?
I haven't talked about any beginnings, and I'm not likely to talk about any beginnings, and I'm not likely to talk about any ends. We don't know anything about beginnings and ends. It's like a television show, and we're right in the middle.
You're not into what you call the Big Bang Theory?
Of course not. What a stupid theory.
But you say that it was created of a piece that you can't grow galaxies. You know that galaxies happen.
No, they grow by themselves, though. You can't grow them, but they grow by themselves. The exterior decorator is the gardener.
So what is your disk man?
What?
The big field of the disk outside the cluster. You're talking about a cluster. I mean, you showed us.
We have disks on galaxies. We don't have disks outside the clusters. The clusters of galaxies do not have disks. The galaxies have disks. Some of the galaxies have
I
disks.
thought that was that galaxy you showed us with a big cluster.
That's a galaxy. Now what I want to know from you is, which size galaxies would you expect to have disks? The great big ones, the medium-sized ones, or the dinky ones? You get to vote on this. This is a multiple choice. Which size galaxies do you expect to have disks? Dinky ones, medium-sized ones, or big giant ones? How many for big giant ones? Put up your hands. How many for dinky ones? Please put up your hands. How many for medium ones? Please put up your hands. Well, it's the medium ones that have disks. The great big ones don't have disks, and the dinky ones do not have disks. And I think that the reason the dinky ones do not have disks is because they don't have enough stellar winds to blow the remaining hydrogen in the dust out from between the stars. And I think the great big ones have so much stellar winds that they blow the stuff far away. The medium ones have enough stuff to blow it out of them, but not enough to blow it far away, and they form a hovering layer, and the hovering layer flattens into a disk. Now the small Magellanic Cloud, that's one of our neighbors, the small Magellanic Cloud has 30% dust and gas left between the stars. 30% dust and gas left between the stars. The large Magellanic Cloud has 15% dust and gas left between the stars. Our galaxy has 2%. The Andromeda Galaxy, which is bigger than ours, has 1%. The great big galaxy in the Virgo cluster, M87, doesn't have any that we can see.
What's the name of our galaxy?
What?
What's the name of our galaxy?
Milky Way. What does galaxy mean in Greek? It means Milky Way. We live in the Milky Way, Milky Way. It's like chop suey. It's like chop suey. Suey means to chop. Chop suey means chop chop, and it's made by the Chinese and eaten by you guys. There's no such thing as chop suey in China, you know. That's where I came from. There's no such thing there. Yeah.
I take it these stellar winds, in order to maintain the shape of the disk, must be fairly consistent.
It's a continual thing. It's like a fountain. There's continually stuff being blown out to the hovering layer. Continually gets flattening down into the disk. Now the early disk stars in our galaxy, the early stars in the disk of our galaxy, are 5 billion years younger than the central bulge. The sun is 10 billion years younger than the central bulge. The stars that are forming now are 15 or 17 billion years younger than the central bulge. The first stars in the disk of our galaxy are 1% dusty. The sun is 2% dusty. The stars that are forming now are 3% dusty. There's continually stuff being blown out to the hovering layer. Continually the dust of exploded stars is being blown out. And continually it's getting dirtier and dirtier.
And the relative dating?
He's up.
It's okay. But I'm just wondering, spinning objects exert gravitational force?
No, has nothing to do with spinning.
If you have something in space that's not...
Has nothing to do with spinning.
No.
Gravity sucks and it doesn't pay about spinning. That's a usual American superstition.
If you have a satellite in orbit and you put somebody on that satellite that's not moving, like a space station that's not, has no spin to it, then there won't be any...
That's a different problem altogether. That's because the gravitational field of the spaceship is too small to suck you down.
Okay, but if you spun that object in
then
space,
you're thrown to the outside, not to the inside.
The planets within the galaxy, the hydrogen, the gaseous type planets that are forming within the galaxies, some of that matter must be going to them too. Like, besides being thrown out of the galaxy, shouldn't some of that be coalescing?
You get a whole lot of stars formed in the middle, a whole lot of clusters of stars formed in the middle, and then clusters of stars formed out farther out. They fall in and thrown through. Then the remaining stuff does not form stars for a long time until it flattens into the disk. And then the density builds up. No stars will form out here. The density is way too low. Something has to push this stuff together, besides just gravity pulling it together, unless you have a huge cloud. This thing's big enough for the whole thing to be pulled together by gravity. But these little things won't fall together by gravity. The chairs in this room never suck onto a pile in the middle. They don't do things like that.
So how are these planets being formed, like our own planets in our solar system?
We'll get to that next time. First we have to talk about galaxies. That's for tonight. And then we have to talk about the birth, growth, and terminal elements of stars. And then we'll talk about the solar system. Little by gradually.
Just one more question of the
Yeah.
solar system. You don't have to answer it. If we removed one of our planets out of our solar system, what would it do to the rest of the solar system?
Nothing.
Would our planets still exist the way?
Yeah, they wouldn't even notice.
They would notice one planet missing?
No. I'm reminded of a cartoon. I'm trying to be humble about being proud of being humble and all that jazz. Guess what?
We have a question down below here.
Oh, he had a question.
Sheila had a question.
I just wanted to be sure I understood what you said about stars getting dustier. You mean they contain other things besides hydrogen, more other sorts of things?
getting dustier means that the dust of the exploded stars are accumulating in the disk. And so the disk is continually accumulating the dust of exploded stars. So the earlier stars formed in the disk were only 1% dusty. The stars that are forming now are about 3% dusty. That's just because the dust is being continually blown out to the hovering layer and flattening into the disk.
How does that affect a star, it being dusty?
It allows them to have planets like the Earth and Mars. Isn't that lovely? Well, he's still up.
I'm looking about the dating. You were saying that different things happen at different times, and I'm just wondering how things are usually dated when we're talking solar systems and galaxies.
Well, we didn't have any calendars in those days. I don't know quite what you mean.
Well, you were saying that, you know, this star is 200 million
Oh, you
years,
mean how do the
this
astronomers know how
galaxy
old
is
they
40.
are?
Yeah, yeah.
Oh, well, that they know because of those cyclotrons and bevatrons and all them other trons. They know what happens to things when they collide at certain speeds. And they can calculate the temperature inside the stars. What?
Collisions? You say collisions?
Now, watch it. If there weren't any collisions, there wouldn't be any stars.
Uh-huh.
The stars don't collide with each other. The stuff that made into the star, of course it collided, otherwise it wouldn't be a star.
Uh-huh.
Of course it collided. But there were gas clouds that collided. We didn't make it out of superballs. We made it out of hydrogen clouds, and they collided. It's not that I'm against collisions totally, it's just that I'm against destruction derbies. Yes?
So I've heard this phrase a couple of times in the start. Gravity sucks.
Yeah.
Electricity pushes.
Yeah.
Well, so we have this great coalescing machine here.
Yeah.
And but a lot of what you're talking about happens from stars exploding.
We'll get to that a little by gradually, but we're not ready for that now. But that's where the dust came from, and that's what I told you. The big heavy stars explode, and then they make all this dust, and they get blown out to the hovering layer and flatten into the disk. Yes?
Can you go back to explaining how we know how old the stars are?
The way we know how old the stars are is because we know how hard they hit each other in the middle of the stars. Sir Arthur Eddington, way back in the 20s, oh, I shouldn't tell you all this now, well, I will tell you anyway. When I was a kid, it was taken for granted that the chemical mix of the universe was given at the time of creation, if there was a creation, or that it had been around forever, if there was a forever. Those were the only two choices when I was a kid. But Sir Arthur Eddington calculated how hot it is in the center of the sun, because he noticed that the sun is not packaged by the Coca-Cola bottling company. It's packaged by gravity. And if it's packaged by gravity, and you know how heavy it is and how big it is, you can calculate the pressure all the way in. And if you can calculate the pressure, you can calculate the temperature. And he thought the centers of the stars might be hot enough for one chemical element to be made into another. And that was a very unpopular view in his day. And in one of his lectures he said, let those who feel that the centers of the stars are not hot enough for this find themselves some hotter place. I think that's as tactfully as anybody's been told where to go. But in the centers of the stars, we know how hard things are hitting. And we know with our cyclotrons and all those machines, what happens when they collide at those speeds. And we can calculate how long it would take the star to do something rash. They can calculate that. The physicists allowed the astronomers to calculate this. Only the physicists allowed us to do it. What else? Yes?
All the energy in the universe went down into a black hole, got sucked into a black hole. Would the universe be the same as it was pre-Big Bang?
Well, first of all, there wasn't any pre-Big Bang because there wasn't any Big Bang, so what else? But you see, I used to make fun of I've made fun of the Big Bang ever since I heard about it, but I still make fun of it. But I used to make fun of it this way, that the Big Bang people want us to believe that first the good Lord made space and time and left them empty, and then he made the fireball, and then he made physics. No, then he made the fireball and allowed it to explode, and then he made physics. Because if the physics came first, the fireball would have been in a black hole, and it couldn't have exploded. So first he made the fireball and allowed it to explode, and then he made physics. Anyway, I'm not going in for black holes, okay? And the whole universe is not likely to fall into a black hole. There is absolutely no evidence that it's going to happen that way.
Will you have them in your house?
Would I what?
Have black holes in your house? Where do they fit into your cosmology?
What, black holes?
Yeah.
I have no serious objection to black holes, but they're not a big thing in my opinion. Well, I shouldn't say they're not a big thing, they're a very small thing, of course. But they're also not holes.
We have the winds though.
It's cooler with the door open.
They're not holes.
No, what you mean by a hole is something that you can put something in, but it's because it's empty inside. But they're not empty inside. They're already full. And so the only reason you can put something in is because they don't care how much fuller they get, that's all. But they're the fullest things we know about, and so in that sense they're the farthest things from a hole known to man, that's all. Anyway, we're not ready to talk about black holes. That comes with the growth, birth, and terminal elements of the stars. Yes?
If entropy or enthalpy is a way of describing the universe, that it is...
Entropy is simply a measure of the scrambledness of the universe, of the energy, that's all.
That's all, okay. It doesn't pertain to other things that are in the universe, like, for example, the organization in galaxies and in our elements and our periodic tables.
It's related to the scrambledness of the energy, not to the scrambledness of my talk. It's related to the scrambledness of energy. Yeah.
Why is it when you have two hydrogen clouds and when they collide, stars are formed? What's the process?
Well, they don't necessarily have to form stars just because two hydrogen clouds collide. Right. But if a lot of stuff accumulates, if it keeps coming in from all sides, so the density builds up, then stars will form. If you have any mechanism that condenses the hydrogen into big blobs, then the stars will form in the blobs, yeah. Keep going, yeah.
You said you don't deal with beginnings, but you did take us back to where the universe was uniformly hydrogen and helium.
Oh no, I didn't mean to do anything like that.
Oh.
But I did ask you what you would expect to happen if it was like that. I didn't mean to suggest that it used to be like that. I'm not that old. But I'll tell you a story. I was in New Mexico, and somebody was talking about the Big Bang to a big audience. And I was in the audience, and he knew I was in the audience. And he's in favor of the Big Bang, you see. But in the course of his talk, he said that Dobson does not approve of the Big Bang. And the difficulty with that is that he's old enough to know. That's called getting my number and dialing it. Yes.
Are new galaxies being formed?
Are what?
New galaxies being formed.
Now that you see, I think there are new galaxies being formed, and there's a lot of evidence that there are new galaxies being formed, but most of the academic community has bought into the Big Bang. They have taken it hook, line, and sinker. In fact, several sinkers have already been swallowed. But according to their model, you don't have any new galaxies being formed, and there's not anything to form them out of. According to the Big Bang model, all the galaxies should have formed in the first few weeks. But there are a lot of other troubles with the Big Bang.
Model changes.
We'll get to some of the troubles with the Big Bang. Yes?
I just wondered about this apparent expansion of the universe, that everywhere you look, it looks like things are...
We'll get to that too.
Okay.
These interesting things we're saving. First, I want to start with our feet on the ground, okay? I don't want to start flopping around. We're going to start with our feet on the ground. We're going to find out what the universe is made out of, on what kind of energy it runs, and what you would expect to form if it went like that. So we're going to do, so we did galaxies tonight, and we're going to do the birth growth of terminal elements of stars, and then we're going to talk about solar systems, and then we'll be ready to talk about the interesting things like the expansion of the universe, whether it really is expanding, whether it's finite or infinite. All these very interesting things will come up as soon as we've got our feet on the ground.
I have another question.
Yes?
When you're talking about the original forming of the gas clouds and the turbulence in them,
Yeah?
and then you talk about things falling to the center, wouldn't there be like angular momentum making it swirl rather than fall?
Not unless something passed it. You cannot make angular momentum without it. By itself, you can't do it. You can't make it by itself. Angular momentum is always half of something. There's always something else spinning the other way.
So the original collapse of the gas cloud would be straight in?
Not necessarily. It depends on who went by first.
First?
Never mind first. Who went by previously? Who went by previously? If galaxies pass each other, when I show you the slides, that'll be dreadfully clear. You see these pictures of galaxies passing each other, and right away you can see that as they pass each other, they spin each other, and as they spin each other, they form spiral arms. You see the whole thing. And then I'll show you some pictures of real live galaxies playing contact sports. Stars indulge permanently, so far as we can tell, in non-contact sports. Galaxies play contact sports.
Question?
Yes.
Did you say anything about entropy besides that it's the law?
I said it tends to a maximum.
I know, but why?
But what?
Why?
Why? Oh, yes, I should say why. It's because scrambledness is a problem that arises in a large community. You cannot shuffle the ace of spades. You cannot shuffle the ace of spades. You can shuffle a deck of cards, you can shuffle two decks better. The bigger the association, the more shuffled it can get, right? Well, the universe is a very big association. It could go way down the tubes. And it's on its way. Well, we'll save it at the end, but not yet.
But then you said entropy is just about energy.
Yes.
So matter, matter being all over the place, that doesn't count because why is that, John? Because you can.
But you haven't figured out what matter is yet.
The other question I had, John, was.
Which of us are they laughing at?
I don't know. I don't know what they're laughing at.
Anyway, go ahead.
Gravity sucks electricity pushes.
Yes.
I'm puzzled about the positive-negative.
Well, that's okay. We'll get to all those things. When we get to the interesting stuff, that'll come in by itself. Anything else?
To have gravity, don't you have centrifugal?
What?
In order to have gravity, aren't you looking
No,
at
you don't have to have centrifugal force to have gravity. No, it is not related to spin. Now let me tell you all something. I make fun of you like this just so that people will understand that that's not the right answer. You understand? It's just for the fun of it.
Yes.
If any of you get embarrassed, I've done a very simple thing, okay? I make fun of you like that just so the class will understand that that is not the right way to go about it. Spinning has nothing to do with gravity. The Earth does not have a gravitational field because it spins.
But you do have two forces when you're spinning an object.
That's correct. What do you mean two forces?
Well, centripetal and centrifugal forces. But if you grab a pail of water
But gravity
and
is
spin it
not,
around you,
gravity is not the centripetal. Okay? It is not it. When you get thrown out of the merry-go-round, it's not because gravity is pulling you toward the middle. It's because the merry-go-round is going around, and you're trying to go straight. It's because you're trying to go straight, and the merry-go-round has to keep making you curve, that you think you're thrown out. You're not thrown out, you're just trying to coast forward.
But
the physicists won't even allow that it's a force, you know. Yes.
Do you know what gravity is?
Yes, I do.
What is it?
I'm not going to tell you yet. I'm not going to tell you because I'm sure that your feet are on the ground. But let me tell you all something. We send all the kids to high school before they go to the university, so they'll all be polite when they get to the university and will not ask the professor what gravity is. He has no idea what gravity is, and he doesn't want to be quizzed on it in class. But yes, I do know what gravity is, and it's very easy to tell you, but not all of a sudden. Somebody up in Oregon asked me what energy is. So I told him right away what energy is. So then he says, so you really don't know what energy is? Oh, then I got on him. Oh, Lord. I gave him a tongue lashing. Only he doesn't hear it. Goes in one ear and out the other faster than it goes in this one. All right, any more questions?
what is that a factor of that it goes in?
What?
How does it go out faster than it comes in?
I'm not sure. I have a delay mechanism in mind. All right, now shall we do the homework for the next time? Let's just start with the birth, growth, and terminal elements of stars. What time is it?
It's about 25 to. You got lots of time.
All right, we've got time. Have we finished with galaxies? You got them all sorted away. All right. You see, there's this difficulty about the universe. You cannot understand about galaxies without already understanding about stars. And you cannot understand about stars without already understanding about galaxies. And there is this difficulty with human knowledge. And I have to take off my hat when I do wear a hat to the teachers in this world. Because if the kids knew everything except one little point, the teachers could present that one little point, it would be all over. That would be very easy. But in order for the kids to understand this, they have to understand this. And in order to understand this, they have to understand this. And I don't know how they manage. But mostly they fail. All right, the next question is, why is the sun hot? What makes the sun hot?
It's burning.
It's not burning.
Nuclear fusion.
Nuclear fusion. At what temperature does nuclear fusion begin? At 10 million degrees. I asked what made it hot. Fusion keeps it cool.
It's not burning? Like it's not
No, it's not
oxidation of
burning.
any kind?
It's not burning.
So gravity makes it hot.
Gravity makes it hot, and nuclear fusion keeps it cool. All right. Now, long ago, it was a big cloud of hydrogen falling together. Now you know how things fall. They fall faster and faster and faster and faster. What stopped it?
Collision.
Collision. The hydrogen falling from this side collided with the hydrogen falling this side. What did that do to the temperature? It raised the temperature. Now, do you think it fell to a sudden stop or a cushioned stop?
Very sudden.
What?
I think it's fairly sudden.
No, it's not sudden. It's a cushioned stop. The pressure gradually builds up until it can't fall any faster. Now, what shape do you suppose it will be at that time? What?
Egg shape.
Egg shape with a yolk.
How about spiral?
Flat?
Anyway, no, there's no reason why it should be very flat, but it was spinning, so it would have been a little flattened, yes, it would have been a little flattened because it would have been spinning. Our sun is out in the disk, and we think it used to spin about 200 times faster than it spins at the present time. At the present time, it spins around once a month, approximately. All right? So the sun fell together until it was too hot to fall any further. What is the next thing that it did?
Transmogrified.
It what?
It changed itself. It got heavier. Well, the hydrogen changed to helium.
No, it didn't. What is the next thing that the sun did?
Before fusion reactions?
What?
Before the fusion reactions?
Never mind fusion reaction. What is the next thing that the sun did?
Started cooling.
What?
Started cooling?
No, it did not anything like that.
Expanding.
It what?
Expanding?
No, it didn't. Now, there are certain astronomical observations which can be made with the bare eyes. One is that the sun is round. What made it round? Gravity made it round. The other thing is that it's shiny. You must have noticed. The next thing the sun did is to shine away the extra energy at the edge. Got it? It fell together by gravity until it had too much energy inside to get any smaller, and then it shined away the extra energy at the edge. Does that make it bigger or smaller, hotter or cooler?
Let's make it cooler.
How many think it makes it cooler? Put up your hand. Never mind, put it down. I'll tell it to you again, and this time listen up. The sun fell together by gravity until it had too much energy inside to get any smaller and hotter. Then it got rid of some of that energy. What happens to it?
Got smaller and hotter.
Gets smaller and hotter. Oh. Keep your computers plugged in. It falls together by gravity until it has too much energy inside. If it gets rid of that energy, it gets smaller and hotter. And it keeps on getting smaller and hotter until what? Until what?
It's all gone.
No.
No? Blows up.
No, it doesn't. Until hydrogen fuses to helium. You see, you mention all these things at the wrong time, and then you just shut up. Then it starts fusing hydrogen to helium. Does that release energy or absorb energy? It releases energy, and it's an enormous amount of energy. What does that do to the sun? Does that heat the sun or keep it from getting hotter? It keeps it from getting hotter by keeping it floated at the middle. If you could shut off the fusion, the sun would fall together by gravity and keep on getting hotter and hotter and smaller and smaller and hotter and hotter. And then it might melt the earth. That's okay, we'll get melted anyway, but not yet. So
you're saying its energy outlay would increase, and it's as its size decreases, the energy outlay.
Yeah.
And the apparent.
That is to say, the temperature goes up. As the sun gets smaller, the temperature goes up. But right now, it is run into a delay mechanism. It's run into the delay mechanism of having too much fusion going on in the middle, and the energy released by that fusion has to leak out to the edge and get away. Now the question is, why does the sun take such an unconscionably long time a-dying, as Shakespeare would say? Why does the sun take such an unconscionably long time a-dying?
Use up all the
Why can't it do it fast? Why can't it have done it by Friday? It's because it takes a long time for the energy released at the center to leak out to the edge and get away. Now I'm going to give you some numbers, and I want an answer. let's just suppose that the center of the sun is at 15 million degrees Celsius, and that the surface is at the freezing point of water, 0 degrees, okay? 0 degrees Celsius and 15 million degrees Celsius. And let's presume that the diameter of the sun is 1 million miles. What is the temperature gradient per mile? How much does the temperature fall in 1 mile? 15 million at the middle, 0 at the edge, 500,000 miles away. What's the thermal gradient?
30 degrees.
30 degrees per mile. Is that clear? The temperature gradient in the sun is only 30 degrees per mile. Now if you had a sleeping bag a mile wide that way, and a mile wide that way, and 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 you were 30 degrees too warm, what is the chance of cooling off before breakfast? Don't you see what a problem you'd have? 30 degrees per mile, and the sun has to leak that energy from the center to the edge. It takes about 1 million years for the energy released at the middle to leak out to the edge and get away. And that's why. What?
How can you know what the temperature gradient is?
Yeah.
This from that one
Sir Arthur Eddington noticed that it was packaged by gravity and not by the Coca-Cola bottling company. And if you know how big it is, and we know how big it is, and you know how heavy it is, and we know how heavy it is, you can calculate the pressure all the way in. And if you can calculate the pressure, you can calculate the temperature. That was done quite a long time ago by Sir Arthur Eddington.
What was he working from?
From his smarts.
From what, Galileo or something like that?
Oh, you don't have to go that far. You just have to know that it's packaged by gravity.
Just from the
you just have to know how big it is and how heavy it is, and you can calculate the whole thing.
Measure it up, weigh it.
You don't have to do all that. We already do all that.
Yeah.
How do we know that?
I'm not sure how we know how heavy the sun is. Yes, I do know how we know. We measured the gravitational field between two half-spheres of lead. Okay. We measured the gravitational field between two half-spheres of lead. And then from that, we can calculate some other things, what the gravitational constant is. Then if you know how far away the moon is and that it's orbiting the Earth, you can calculate the weight of the Earth. Anyway, the first thing we did was to measure the gravitational field between something whose weight we knew. Anyway, the history of science is very long, you know. There have been smart people for a very long time working out all these very interesting problems for a very long time, and we owe them an enormous amount. We're born late in time, and all these things have been worked out by this enormous amount of effort. And we come in and we just take it all for granted. We don't even take it seriously. You see, a long time ago, the energies were straightened out in the Orient and India. They figured that these different kinds of energies, gravitational energy, kinetic energy, radiation, electricity, and magnetism, they even had them in order. They even had them in the right order. And then Mendeleev and some other people put the chemical elements together in a table. That's a lot more recent. That's only a couple of 100 years old or something like that. But all these things have been done, and we come in late in time, and we just take it all for granted. We hardly even look at it in a book. That's because we didn't have to figure it out. Is that lightning?
Yeah.
Well, hot diggity dog.
Does it tend to follow you?
Not unless I'm running with a 24-inch telescope.
Ooh, dangerous.
All right, so we're talking about the birth, growth, and terminal elements of stars. So the hydrogen is being fused to helium in the middle of the sun, and gradually the energy is leaking out to the edge and getting away. This has been happening for 5 billion years. It'll go on for another 5 billion years. And then all the hydrogen will be gone in the middle. What will keep the middle floated when there's no more hydrogen in the middle to keep it floated? What will keep the helium floated?
Gravity.
Gravity does not work at cross purposes.
Can the helium be fused to some other lesser element? Just go
Yes.
one step further?
Gravity, but first the helium core will collapse. It's not going to fuse all of a sudden, nothing like that. The helium core is going to collapse to the density of about 2 concrete mixing trucks filled with concrete with both drivers in a 1-pint yogurt box. Will that be warm or cold? You can find out by just trying to put the drivers in a box. And then you're going to put these 2 concrete trucks in on top of them. All right, it's going to be hot in there. The fusion rate around that core will be all out of control. Right now there's a governor on it, because if it fuses too fast it will bloat. And if it bloats it slows down. If it slows down too much it'll collapse. If it collapses it speeds up. Got it? So right now the center of the sun has a governor on it. If it bloats too fast it'll slow down. If it doesn't bloat fast enough it'll speed up. So it has a governor on it, but at that time it will not have a governor on it. The center will be collapsed with this enormous density. It'll be very, very hot, and the fusion rate around the core will be all out of control, and it'll cause the outside of the sun to swell up to a great red balloon until it fills the present Earth's orbit. Got the picture? The sun at that time will be as big as the whole Earth's orbit. By that time the sun will have lost some mass and we will have drifted away to about as far away as Mars, and the Earth will be molten. Cheer up, things are sure to get worse.
How old will it be?
How what?
How old will it be?
It'll be twice as old as it is now.
So,
The sun is now a teeny bopper, about 5 billion years old. When it gets to be about 10 billion years old, it swells up to a great red balloon and we get to be molten about where Mars is now.
so when fusion started happening and you started getting the hydrogen becoming helium, was there an analogous thing as to what would maybe happen when it turns from helium to whatever number 3 is?
We haven't done anything like that yet. We haven't done that yet. We are not there yet.
But I mean,
your feet are still floating on the ice. Hang on now. So, what's going to happen to the extra helium that's produced by the fusion around the core? Where is the extra helium going to go? Come on, come on. Where's the extra helium going? Why would it go up?
Balloon.
We've got helium in the core condensed down to the density of 2 concrete mixing trucks in a 1-pint jar. And it's not going to go flying up.
but is it maybe going to do, you know, another level of fusion and turn into
No, it's not going to do anything like that. The hydrogen, the fusion, the helium that's produced by the fusion around the core is going to add itself to the core. Because as soon as it doesn't have any hydrogen mixed with it to fuse and float, it will collapse onto the core. When the core gets more and more helium added to it, will it get bigger or smaller? Bigger. No, it'll get smaller. It will get smaller. Its size is not determined by temperature now. It's not determined by how much stuff there is. Well, it's related to how much stuff there is. But gravity likes big packages. The United Parcel Service takes the rest. Gravity likes big packages, and the more you give it, the harder it squeezes. So the more helium we add to the core, the smaller it gets and the hotter it gets, and eventually it gets hot enough to fuse helium to carbon and oxygen, and that goes off explosively. That goes off explosively. Now that's a helium bomb. The most energetic nuclear bombs are hydrogen bombs. Hydrogen going to helium. The second most energetic nuclear reaction is helium going to carbon and oxygen. So this is a helium bomb the size of the Earth. Will it blow up the great red balloon? You get to vote. How many think it'll blow up the great red balloon? Please put up your hands. How many think it will not blow up the great red balloon? Please put up your hands. Those who said no, please tell me why. You don't get to come. Yeah?
I just put my hand up, but I didn't see a lot of big red balloons around. Because they're common.
What?
Because big red balloons are common. Big red giants are...
No. No. Why will it not blow up the big red balloon?
Gravity?
Gravity. Gravity has it by the short hair by now, okay? The gravitational field on that helium core will be so strong that if you were on it, you would be as flat as if we laid you out in your bikini and used a battleship for a rolling pin over you. No bones would stick up. It's against that gravitational field that this explosion must blow, and gravity contains it. It probably won't even be noticed from outside. However, that's the thing that happens. Then the carbon and oxygen core will reconvene after the explosion inside the great red balloon. The carbon and oxygen core will reconvene, and gradually the outer stuff will puff away at the equator. See if you can find a copy of the Ring Nebula in there. Look up in the index, see if they got the Ring Nebula in there. I want a picture of the Ring Nebula. All right, now you can ask me some questions.
So helium doesn't have any steps in the middle when it changes to explosively to oxygen and carbon?
Well, this will do. This will do. Thank you. Where did we get water? The sun will, see the star at the middle, that's a dwarf star made of carbon and oxygen, and this green in here is oxygen coming off the surface of it, but this is the last puff of hydrogen puffed off at the edge. What happens is that the hydrogen puffs away at the edge, the hydrogen and the helium puff away at the edge, thank you, and until the central star is exposed. The central star in the Ring Nebula is blue. It's 7 times hotter than the sun. Now what happens on the outside is that when it gets all puffed out like this, whole atoms form, and then that puffs the outside away. And then the next layer comes out, and when whole atoms form in it, it puffs it away. And we think the Ring Nebula star used to weigh 8 times as much as our sun, and it's already puffed away at least 5 times as much as we have in our sun. And the dwarf star at the middle now is made of carbon and oxygen, and carbon is coming off the outside. No, not carbon. Oxygen is coming off the outside, and that's what makes it green inside the loop. Now, when the star ends, when these little stars end, they're made of carbon and oxygen, but their way to explosion to be diamond. Now it might be, after they cool off to black dwarfs, it might be that on the surface we might have mountains of diamond. Okay? Now just suppose we're in the Starship Enterprise, and Spock's tricorder says, we're going by a black dwarf star, and there are mountains of diamond on the surface 3 feet tall, and the crystal faces are 2 inches across. Shall we go down? You get to vote on this. How many are going down? Please put up your hand.
Depends on the commercial sponsorship.
What?
Depends on who's got the commercial sponsorship.
I'll go down.
I'm not going down because on the surface of that star you would weigh as much as 1 U.S. battleship, and you would be as flat as if we'd use a battleship for a rolling pin over you.
You have all of that?
And the, what? the diamonds that you'd want to harvest would bruise your flattened legs when you put them in your pockets. Now I have another reason for not wanting to go down. Scotty has trouble with the transporter most every Friday. And if you weighed as much as a battleship, well, what's the chance? All right, that's what happens to little stars, and you can remember it because you have a verse. What's the verse? Come on, you kids, what's the verse about stars? Twinkle, twinkle, little star, how I wonder what you are above the world so high like a diamond in the sky. Little stars go to diamond. I don't know how she knew that. I don't know how she knew that.
You said little stars go to diamond?
Little stars. I thought we just went through that.
What happened to the helium cores, though?
It went to carbon and oxygen. We already did that. What about you?
It all goes at once. It's a sort
It goes
of a fusion
explosively
type
to carbon and oxygen. All right. Now what happens to bigger stars? Do they go through the same routine at the beginning? Thank you.
What was your question again?
We handled little stars. What happens to bigger stars? Do they do the same thing at the beginning? Come on, yes or no?
I think so, yes.
Yes, they do the same thing at the beginning. They do the same thing at the beginning. They fall together until they get hot enough to fuse hydrogen to helium, and then the helium goes to carbon and oxygen, but it doesn't explode. The explosion comes later. It goes quietly to carbon and oxygen, and then it explodes later, maybe to sulfur or silicon or something. Anyway, the explosion comes later, but it goes right on through the atomic table until the center is iron. Now, iron is the stupidest stuff in the universe. There is nothing so stupid as iron. Iron has no nuclear energy available to it to push back against a gravitational squeeze. Iron has no nuclear energy to push back against the gravitational squeeze. So this time gravity gets it by the short hair and squeezes it down to the density of 100,000 US aeroplane carriers, all covered with aeroplanes, and sailors on parade squeezed into a 1-pint mayonnaise jar. Now you have to think what trouble you have in the afternoon. You spend all morning putting in one of these airplane carriers into your mayonnaise jar, and you didn't take the mayonnaise out first. But don't make no never mind about the mayonnaise. And now you've got to put a second one in the afternoon, and you have 100,000 to go. Now when these stars collapse like that, the energy released in the collapse blows the rest of this outer portion of the star all over the galaxy. See if you can find me the Crab Nebula. Look up at the index crabs. They'll only have one crab in there.
Nickel and cobalt do stars. Nickel and cobalt are similarly stupid, or I'm just wondering if there might be a relationship between.
Iron is really the major one that you get in these in the cores of the stars. There's lots more iron than cobalt and nickel. But the iron asteroids have about 5% nickel, but it's mostly iron. But they're all in that same region in the atomic table, yeah.
And they all have one relationship, maybe to gravity, and another one to electricity.
What?
Aren't there? Aren't they the ones that are magnetic, like? Aren't those the three magnetic elements?
No Crab Nebula there. I saw a picture of the Crab Nebula in there. No, Crab Nebula, crab, C-R-A-B, crab. I saw a picture of it.
Like magnetograph, iron, nickel, cobalt, I think. Not cobalt. There's three.
Anyway, the Crab Nebula, I hope we can find a picture of the Crab Nebula. There it is, there's a picture of the Crab Nebula. Now this is the stuff that was blown away by the collapse of a star on the 4th of July, 1054 AD. This is the way it looks after 900 years. If Methuselah saw it blow up, this is how he'd see it before he died. Now, the star at the middle there has a bit, whoops, I'm sorry, he knows the number. The star at the middle has a density of 100,000 battleships in a 1-pint jar. And if you had a piece of it the size of a softball, you would not be able to pull your hands away. Your hand would weigh 500 pounds, and you could not pull it away. And as the thing fell through the sidewalk, it would scrape your bloody fingers off on the stones, and it would fall faster through the rocks than a super ball falls through the air, and it would make this lovely crunching sound. And the seismologist, the geologist would have a ball, a very small ball, and it would go right on through to someplace out in the Indian Ocean or someplace wherever you're opposite, and then it would come back again. Now, if we had a bigger piece, the size of a basketball, you could shoot a pistol here, and the bullet would buzz around in orbit. But you would have to have a sign there, keep children away. Because if any child got close enough, he would be spread over the surface as such a thin scum that the FBI would not be able to find him.
How close could you get?
I have never tried. Now, if we had one of those stars, they're only about 10 or 12 miles in diameter. They're only the size of they're a little bigger than San Francisco, nowhere near as big as Los Angeles. So if we had one in this direction from us, which direction would be down? This direction would be down, and the Earth would be spread over the surface of it about as thick as the cover of a book. The whole Earth would be spread over the surface of this little ball, 10 or 12 miles in diameter, about as thick as a scum, about as thick as the cover of a book. Now, the interesting thing about these explosions is they're really collapses, but it's the collapse that drives the explosion. And the interesting thing about these stars is that they're the ones that make all the heavy elements. Up to iron, they're made in the stars, and beyond iron, they're made in the explosions. But the interesting thing is that the companies that make the heavy elements distribute them. The United Parcel Service does not make the packages that it delivers at Christmas time. Somebody else makes the packages, and all they do is deliver. But these heavy stars make the heavy elements, and then they deliver them. Okay, now you can get on my case again. Go ahead.
I want another contract.
You what?
So, what percentage of heavy stars has expired?
What does he say? I can't tell.
What percentage of heavy stars have exploded at this point?
Oh, I don't think we know about that. I don't think we have any information on what percentage of the heavy stars have exploded, but we do know that stars beyond a certain mass are scheduled for explosion, and our sun is not. Our sun is too small to go like that. But the heavy stars we think will go like that.
So you said that the things lighter than iron are made internally, and things heavier than iron are products of the explosion?
Yes. Up to iron, they can make them in the stars. But beyond iron, they're made in the explosion, yeah. Like gold for our teeth and platinum for our crucibles, they're made in the explosion. Yes.
Is Jupiter a small star?
Yeah.
What's its how much mass does it have compared to something like the sun?
Not very much. There's room for 1,000 Jupiters inside the sun, and for 1,300 Earths inside of Jupiter. Well, now we've covered the first and second classes. I suppose I should tell you a few other things, though. When these stars collapse like this and explode, the explosions are not symmetrical. And the neutron star that's left over goes bebopping off And they think that half of them are going faster than 300 miles a second, and they can escape from the galaxy. Escape velocity from the galaxy is 300 miles a second. And they've got some of these neutron stars going 450 miles a second, and they're headed out. But you can ask me some more questions, and then if you don't have any more questions, we're supposed to scram. And then next time, we're going to have to show slides. We're going to have a projector. Somebody has to come up with a projector, one of those ones that goes round and round, not one of these.
Right.
Not a Ferris wheel, a merry-go-round one. And then I can show you slides, and then we can talk about how the solar system is formed. And you have to think of how the material in the solar system gets sorted so the planets near the sun can be made of iron and rock, and the planets farther out could not be. Yes, what?
Now, I got lost here. We have the collapse. Gravity keeps everything collapsing, and yet the elements are flying out. How can that happen?
That's because of the energy that's released in the collapse. So let me tell you how much energy it is. Now brace yourselves, you will not be able to handle it. You will not be able to handle it. I'm going to talk about the energy by how much it weighs. The energy of an atomic bomb weighs 1/30th of 1 ounce or 1 gram. 1/5 of a teaspoonful of water is the energy of 1 atomic bomb. Enough to vaporize Berkeley. The energy of the St. Helens explosion in 1980 was 1 pound. That's 500 atomic bombs worth. The energy of the explosion that blew Crater Lake was 42 pounds. It blew 35 cubic miles of rock to powder and put them in the stratosphere at 80,000 feet. That's 42 pounds. The energy which the sun releases each second is 4.5 million tons. Each second, 4.5 million tons. It's been doing it for 5 billion years of seconds. It will continue for another 5 billion years of seconds. And when one of those iron core stars collapses, in 3/4 of 1 second, it releases 100 times as much energy as the sun releases in 10 billion years. I told you you couldn't handle it. That's why they go away. And that's why all the heavy elements are made in that explosion. The energy released and the number of neutrons that are dumped out through that cloud is so great that all these heavy elements are born at that time. That's when all those radioactive elements are born too. All those things are born at that time. Yeah.
During that explosion, they're still under the effect of gravity.
Yes, but it doesn't give a damn about gravity at that time.
This is kind of a silly question, but when I was a kid, there was a big talk about anti-gravity and building machinery.
Electricity is anti-gravity, and we'll get to it. And the people that are talking about anti-gravity are just jerks. We've known about anti-gravity for a long time.
We don't have it yet.
These people are just wound up on some other thing. I don't know who winds these people up in the mornings, but...
Wasn't it the World's Fair, Seattle World's Fair?
What?
Was that the big thing?
What?
Seattle World's Fair, they were touting anti-gravity then and all that.
Electricity is anti-gravity. Now knock it off. There aren't any other anti-gravities. Now I guess you can all scram, but remember what the homework is. And is it time to go?
When you're done, I've got some announcements to make.
All right, you can get up here and make your announcements.
Okay, for the people that
Get
came
up in
in
front,
early-
make your announcements.
All right, yes sir, yes sir, yes sir. For the people that came in late, I've got 2 things. There's a book back there I'd like to have you sign, and if you'd like to make a donation, give it to John or put it in the hat over here.
Put it in the hat.
Right there, and we'll have this again tomorrow, 7 to 9, same place. You're all welcome, and we're going to be grinding telescope mirrors out at the house, hopefully, tomorrow from 1 to 4 if it's nice. And we were going to have the telescopes out tonight to show everybody the sky, what's out there, but it sounds like all we can see is lightning, so we'll probably blow that off.
All right, now tomorrow I'm going to have to give you a slideshow. I have to give you a slideshow at first with a whole lot of pictures. We'll talk about the slides and all. And then afterwards we have to talk about the solar system. And we have to talk about the tidal effects of the moon on the Earth, and the tidal effects of the Earth on the moon, and the tidal effects of the galaxies and so forth. So we have slides, tides, planets, and people next time. Thank you.
No, it isn't actually. Is that fellow's there with the gray shirt? The guy with the gray shirt. The guy waving his hand. Pardon me? No, it's out in Mirror Lake. The telescope grinding. The telescope grinding or the cosmology? Is it 7 o'clock tomorrow?
Otherwise, you'll be grinding telescopes, I guess. Otherwise, you're grinding telescopes at something in Mirror Lake.
In Mirror Lake, yeah. And you won't be able to miss it. There's going to be a green and white place with cars all